Okay, let's unpack this. For anyone following cutting-edge physics or, well, even AI these days, you've likely bumped into this huge challenge. How do we understand really complex systems, where countless tiny interactions somehow lead to these big visible behaviors we see? Today, we're doing a deep dive into statistical mechanics. It's this really elegant, probability based way to do just that. It truly bridges that gap, doesn't it, between the sort of chaotic micro world and the reality we actually observe. So, our mission today is basically your shortcut to getting how these statistical methods, how probability theory, how they're not just abstract math, but real tools we use on huge groups of tiny things, like atoms or molecules. And that reveals the big properties of matter. It's about explaining things like temperature, pressure, all from the collective jiggling of atoms and the applications. They pop up in some surprising places. We're incredibly lucky today. We have a Nobel laureate with us, a real expert in this field, to guide us through the core ideas, these things called ensembles, and just how wide its influence really is. So, at its heart, statistical mechanics explains matter, the big stuff, based on the physics of the small stuff, the atoms moving around. But where did this powerful idea, this really unique way of looking at things, actually start?
Well, what's fascinating is how early the groundwork was laid. I mean, long before we could really even prove atoms existed. Daniel Bernoulli, way back in 1738, he essentially planted the seeds for kinetic theory of gases. His idea was gases are just countless tiny molecules whizzing about. Their impacts, that's pressure. Their kinetic energy, that's heat. That was a huge aha moment, linking something you can measure, like pressure, to unseen microscopic action. Pretty radical for the time.
So it started there with this amazing intuition about gases, and then I suppose it just grew rapidly with some key figures building the framework.
Exactly. Things really picked up speed.
Yeah.
You had James Clerk Maxwell in 1859. He came up with the Maxwell distribution. That tells you how molecular speeds are spread out, the first actual statistical law in physics. Then Ludwig Boltzmann. He gave us that fundamental link between entropy and microstates. Entropy not just is disorder, but related to the number of ways the microscopic parts can be arranged for the same overall state. And Josiah Willard Gibbs, around 1884, he didn't just name statistical mechanics, he formalized it, made it a general method for, well, any mechanical system. It even adapted beautifully to quantum mechanics later on. He really gave us the language.
Wow. That's quite the intellectual journey just to build the foundation. But the real power, maybe the biggest challenge too, is how it actually bridges that gap between the particle level we can't see and the bulk material we can. How do we handle not knowing every single detail?
That really gets to the ingenuity of it. The answer is the statistical ensemble. See, instead of trying the impossible, tracking every single atom, you imagine a huge collection of virtual copies of your system. Think of them as independent copies, each in a different possible microscopic state that the real system could be in. This whole collection, this ensemble, it acts like a probability distribution over all those possible states. It lets us predict the average macroscopic behavior statistically without needing every tiny detail. It's about managing uncertainty smartly.
Okay, so these ensembles are the trick, the way to handle the uncertainty, especially for defining something basic like equilibrium.
Precisely. A key type are equilibrium ensembles. These are special because they don't change over time, statistically speaking. That's equilibrium. Now, when you connect this to thermodynamics, we usually talk about three main ones. There's the microcanonical ensemble, fixed energy, fixed particles, totally isolated. Then the canonical, fixed particles, but it's sitting in a heat bath at a fixed temperature, so energy can fluctuate a bit. And the grand canonical. This one can exchange both energy and particles with its surroundings at a fixed temperature and chemical potential. Now, for big, everyday systems, they often give the same answers, which is convenient mathematically.
Right.
But for tiny systems, or systems right at a phase transition, or those with long-range forces, then the choice of ensemble is absolutely critical. It dictates the physics you're actually describing.
It's really something how these fairly abstract ideas lead to such practical results. I'm curious, beyond the basics like explaining gases or solids, where else is statistical mechanics making waves now? Are there unexpected areas?
The applications are incredibly diverse. It really shows how fundamental it is. Of course, it's key in condensed matter physics, explaining things like superconductivity, superfluidity, phase transitions. It's also vital in modern astrophysics, understanding stars, galaxies. Material science relies on it heavily. But here's where it gets, I think, really interesting for someone exploring science today. It's finding serious applications in neuroscience, helping understand how networks of neurons behave collectively. And in machine learning, people are using statistical mechanics concepts to analyze deep neural networks. Think about the network's parameters, the weights, as a complex system. Statistical mechanics can offer insights into how it learns, why it generalizes. It even shows phase transitions during training sometimes. It's becoming a genuinely cross-disciplinary tool for tackling complexity.
So this deep dive really highlights how statistical mechanics gives us this powerful, probabilistic way to grasp collective behavior. It connects that, well, almost unimaginably complex microscopic world with the macroscopic reality we experience every day.
Exactly. Ultimately, statistical mechanics is this amazing toolkit that lets us predict, with remarkable accuracy, the behavior of systems far too complex to ever observe completely. We do it by embracing probability, by looking at averages, and that maybe raises a final thought for you, the listener. How might this whole approach finding order in apparent chaos through statistics change how you think about uncertainty, especially in other complex systems you run into, maybe in economics or biology or even just everyday life? It's a powerful perspective.